Well, hi, this is Samuli Ahonen from Visual Components, and welcome to this Visual Components 4.0 webinar. Today's topic is about component modeling, and you will require this Visual Components Essentials with Modeling Pack version to do the things that we will cover today. The agenda for today is basically the modeling tab. Previously we have covered the basics of the home and drawing tab, and in the future we will also cover the program tab, but today we're going to focus on the modeling. We will first take a quick look on the component structure, what it actually means when we say visual components component. What is it made of? Then we're going to see the modeling tab overview. We're going to model a couple of example components, and also we will take a look on the physical behaviors and features in Visual Components 4.0. Okay, first about the component structure. When we start to model new components, we need to first understand a little bit what's inside of a component, what's the internals of a component. Component is made out of links. If you think about, for example, a robot has multiple links that can move, and those form the kinematic chain of a robot. Same thing happens in a visual component. Component can also have properties like length, width and height, and each link has its own features and behaviors. Then again, each feature can have its own geometry sets, which can include faces, lines, points, also text, frames and things like that. We will see these more in detail soon. So if you think about, for example, a robot component in Visual Components, the whole robot is one component. It has all these links. So for example, in this picture here, we have highlighted the second link from the robot, and that link, that geometry, the 3D model of that link can be actually built out of multiple features. In this particular example, we have now highlighted this top part because this robot is a parametric robot where we can define the link length. So the parameterization of this component has made so that the middle section feature is actually made longer and shorter as we change the link length, but this end will stay the same, which is highlighted. So there is multiple features inside of this one link. This one feature can be still be separated in smaller parts called geometry sets. So for example, the main body of that motor is one geometry set, and that main body again can have, for example, lots of faces. So this is the basic structure of a visual component. If we see this now on the actual software side, so let's go and load in the same model. So I go to Models by Manufacturer, I browse to Visual Components. Under there I will find robots, and I will double click this generic articulated robot, which is the same one as in the slides. I will go to Modeling tab, and on the Modeling tab I see different kind of panels what we see on the Home tab. Probably the center of everything is this component graph. You can say so. So this is very important to understand this structure and how that structure relates to 3D world. And if I click now here, the generic articulated robot, the whole robot is highlighted. So basically this is the component. This is also the root link of my component structure. So if I hit this expand button here, it expands all my links there. And this robot has in total 6 axes plus the mount plate as a separate link. If I click here, axis 2, this highlighted geometry here is my axis 2, my link 2. Inside of this link, underneath here, we can see the actual content of that link, the features. Features are basically those visible things that you can visually see on the 3D scene. So a component has its behaviors, which is the functionality and the functional side of a component, and then you have your features, which is the visible side of the component. So if I now select here, for example, one feature here, that feature is highlighted there. And building these feature trees will form your component structure and the visual side of it. Okay, so here we can access the whole component by selecting this topmost node. We can access links, and underneath every link it has its own unique feature tree, and in the feature tree we can access features, which is the visual geometry. When you click something in the 3D on the modeling tab, you're basically always selecting directly features. So if you need to select a component, you probably need to first click it to get that component active in the graph, and then you can select the topmost node in order to, for example, elevate the component. So that's the main idea of the component graph. The component graph also includes behaviors of the component. So if I enable this behavior checkbox, under each node it lists that node's behaviors. And for example, under root node we can find all these behaviors. We will talk about behaviors more later, but behaviors are basically the functional description for the component. So we can combine different kind of a behaviors, and each behavior is dedicated to do one simple job. Then also we have properties, and the properties you will only see for under the topmost root node, and that's where you can access your component properties. So this all links to these three what we saw on the slides. So component has its links and properties. Links are here and properties are directly under here. Each node, each link has its own features and behaviors. So the features we can find in the separate lower tree, and behaviors we can find under this collapsible little folder under each link. Okay, that's the overview for the component graph and for the component structure. If we take a look on elsewhere in this user interface on the modeling tab, we will find a little bit different selection of buttons in the ribbon as on the home tab. First we have our standard copy paste delete group, then we have our manipulation group, which is same as on the Home tab, except we are missing PMP. So if you need to do connections, plug and play connection between components, let's say connecting gripper to this robot, you need to go on the Home tab, find that component and plug them together with the plug and play tool. Or same thing, connecting to conveyors together. So that's not what you do on the modeling tab. On the modeling tab you will build new components from scratch or from imported 3D geometry. Other than that, you have your interact, so that you can interact with the component. You have your move tool. You can move whatever you have selected. So if I have selected robot component, I can move the whole component. If I've selected this axis, I could move this axis, except in this case it's locked in place. And with select tool you can make selections. The basic mode, what I recommend to use here is the move mode, or the manipulation mode, move. Okay, then we have our same snapping tool and measure and alignment tool as on the Home tab. Then we have our hierarchy and selected move modes. And this will come handy later, but I will show quickly the idea of that. Let's say, for example, in this geometry feature tree here, this is a hierarchical tree where we have this feature, and this feature. And all of these features seem to be grouped under one grouping feature called transform. Also, we're going to talk about more of these later, so don't worry about if you are a bit lost at this point. So this groups all those together, and if I'm in hierarchy mode and I want to move this feature, I will move that feature plus everything underneath. So I will move also the hierarchical children. But if I switch back to selected mode, or I switch to selected mode, and now you see that it doesn't highlight the children. If I select this, it's highlighted, but if I select the parent, the children are not highlighted. And if I move now this parent, the children won't move together. This will come handy, for example, if you need to rotate this. Now you're rotating the whole group from there. But if you go to selected mode, you can elevate this grouping transform and then rotate the whole group from a different location now. So that's your hierarchy versus selected mode. It also makes a difference in the tree here. So when we are in hierarchy mode, you can already visually see that we would be moving now the whole hierarchical tree, but in the selected mode we would only affect locally to our selection. Okay, then we have our importing tool. We will see that in action later. Here we can create completely new component into the 3D world. I click new and I get new empty component in the world, and I will delete that. Then we can save the selected component and save as the selected component. We can create new links to components, and this is where we can create new features and new behaviors and new properties to components. On top of that, we have simple wizards which will do commonly used things and structures semi-automatically for you. And then we have our origin snap and move. But if we just do quickly a simple component structure, so I will create a new component, I will create a new feature, cylinder. So what happened there, when I click new component, a new component appeared in the 3D scene. There wasn't nothing inside of it, but we added a new cylinder into it, which can be found in this feature tree. So currently we have one link, and under that one link we have one cylinder. On the right side here in the user interface, you will always see properties for the selected item. And the item or the object can be a feature, it could be a behavior, it could be a new component, it could be a link. So this is very essential item in the user interface. Okay, I will select again this feature that we just created. I will make it a little bit higher, for example 500 millimeters. Then I will create a new link. I will get link 1, and I could snap that link on top of there, where I could create a new box, and I could make 500 for this links, for this block length. Here in the structure we can show the kinematic structure of the component. I have some weird graphic card issue or something after my Windows updated. These should be just simple rings, but here it's highlighted a little bit differently. Anyways, so we have created the component with the link with new features, and this link, we can choose this link to be fixed, or it could have a degree of freedom. So when I select the link on the nodal tree, on the properties I can find the joint type. By default the new link joint type is fixed. I could change this to rotational, and now I could choose the axis it rotates around. I will use the Z-axis. I could choose the name of the axis and the controller, which we will discuss later. But already now I have this kinematic structure for my component that I can rotate this link around that center point there. Now in the hierarchy mode, if I would like to move my link, I would move the link origin plus all the geometry underneath that. If I select move mode selected, I'm only moving the selection, which is the link. So I'm only redefining the origin of the link. So what that basically means is I redefine the pivot point for this link. Okay, so that's the simple approach for creating kinematic structures. This is very useless example here, so just some imaginary shapes. So let's do instead something we can maybe relate to a little bit better. So we're going to model a couple of example components which are mostly related to robotics, and also a conveyor which can be or cannot be, may or may not be related to robotics. We won't be creating any advanced logics in this webinar. That can be addressed later. We're going to learn the very basics of component modeling. Let's start with this kind of a workpiece positioner often used with robots, where we have two joints in this kinematics, and we want to import the 3D geometry. So first thing to do, I will clear my layout, file clear all, and I want to import geometry. So I will find this import geometry button up here, and I can browse to the correct file. I will import this positioner step, and importing options are shown instead of properties panel in this action panel. I can modify the tessellation quality, how detailed importing I want to do. If I do extra high quality, I will get more accurate shapes in the 3D model, but also I will get a lot more data. And if I'm about to create very big layouts, I don't want to have all that detail in it. This is a bit of a matter of trial and error. You need to kind of test to import and see the result, and maybe then import it again with different results. That's the easiest way to find the proper tessellation quality. Then we can choose to include hidden features, materials, textures, and markups from the imported file. Feature tree. If I'm importing, for example, a CAD assembly, I would like to get some sort of a feature tree that would respect the original structure. In that case, I would like to get a full feature tree. If I'm not interested in the structure of the original model, I could import that as collapsed, and everything would be collapsed into one big piece inside Visual Components. It is still possible to separate all those little details, but it may take a little bit more work, but also the component is a little bit more optimized in performance-wise if it's collapsed. But typically I use the full feature tree. I organize geometry inside features by material, and then I need to choose the up axis so that the up axis here is the same that it was in the system where this model was originally made. Again, this might be a little bit of a trial and error. You need to just try one. Maybe you reorientate the component in 3D world, or you just import it again with a different selection here. So I will go with these options and just hit import, and it imports the component in the 3D view. And in my case, the Z up seemed to be the correct option. Also, the tessellation quality looks pretty good. The round shapes still look more or less round. So I'm happy with this quality and with this import. Okay. If I click on the component, it highlights the selected feature. And even though I selected here that import full feature tree, we only got one big feature here. And that's how the data was organized in the file. So it's something we just need to live with. But we can now start to separate this model into smaller pieces. If I select this feature in the feature tree on the left side, I can right click it and I can hit explode. That tries to find the next level in the feature tree and separates inside of that feature and separates different geometry sets into features of their own. So now it's easier for us to make selection if we want to make, for example, this little table here to rotate. If you're still not happy, for example, you would like to delete one of these faces or something like that, you can try to go even deeper by right-clicking and hitting explode. And now it exploded that into even smaller details. You can come back by collapsing. And that's how you can separate component features inside of a 3D model fairly easily. This won't be the best approach when you have super big models with thousands of features and thousands of little details. We need to take a look on that workflow later. It's a bit different workflow in that case, but for simpler models, this is where you should at least start with. Okay, so now we want to make this kinematics for this component. So we would like to put this, and that geometry in the new link so that we can create a kinematic link for these. So I use Control button to multi-select features. Then I simply right-click, extract link, and I get new link. Then I click on this table, Control click also that small ring underneath, right click, extract link. Then these two links are siblings, but I need this link 2 to be parented to link 1. Alright, now we need to define the center points in this kinematic structure. So I will select, for example, this link 1, and we should move this link 1 center point somewhere. But now if I move this center point, my whole hierarchy is moving together with it. So you remember this move mode, hierarchy, and selected. So if I go to selected mode, I can change the center point of this link without affecting anything underneath that. So I can simply start dragging from this donut, check the previous webinar for more details about snapping and these commands here, which come handy also here. So I put that center point there. If I put my structure visible, I already see that my kinematic skeleton goes from here to there. Then we need to do the same thing for the link 2. This is not the correct place because now the link 2 would be moving around that point. So I will take same thing and snap it there, for example. With Shift you can force to snap to center points, which is very handy. I want to double check my rotations, that every rotation is now zeroed out. And for the link 1, also the same thing, that my rotations look good. Alright, so the link 1, we want to pivot around that point there. So we will change the joint type to rotational. I will then double check that the axis is correct. So around its local Z, when we snapped it on the face, the Z comes out of the face, so that looks good. You can double check it always from the arrow inside of this handle. If I put X-axis, it would rotate around that, Y-axis around that green arrow there, and Z-axis there. Then we need to choose the name for the joint. So I could rename this, for example, E1, as in external axis, and the controller, I will create a new servo controller. This will actually now create our first behavior. So if we check our behavior list, it shows that we have now new servo controller created here. So that was created when I chose here create new servo controller. Now for the remaining axes, we can associate those axes to the same servo controller. So to finalize this, we just double check that everything makes sense. So minimum limit -180, maximum 180 looks good to me, max speeds and so on. Then we do the same thing for link 2. So the joint type for this is rotational around its local Z again. The joint name is E2. Controller, we don't create this time new servo controller, we use the very same one. And the minimum limit could be -360, maximum 360. Okay, that's that. Now we can test this with the interact button, that it tilts nicely there, and it tilts and rotates nicely around there. If we had to make corrections, for example, if this wouldn't be the rotation axis, it would be somewhere else, I would go select my link 1, move, and for example move that center point here. Then if I interact now, it rotates around that new point there. If I had to elevate the whole thing, for example, I would replace this geometry with a little bit higher stand position. I would go and select link 1 and in hierarchy mode move this whole hierarchy tree a little bit higher. So the pivot point plus all the geometry and all the sublinks move together with it. And now it rotates there like that. But I will take this back down to center there with control. While translating that, I was able to snap it in right place. Okay, this component is almost ready. We need to use the wizard to finalize this with the correct behaviors. So in order for this component to communicate with the robot, it requires some interfacing behaviors. That could be done through behaviors here, but position is a very common component, so there's a wizard. So let's learn first these wizards. So I will choose positioner. I will do workpiece positioner. The other option is robot positioner. And the flange link, basically the last link in my kinematic tree, is this link 2. It figured it out automatically, but here is where you can manually choose it. And then I just simply hit apply. And it adds this suitable robot interface there so that we can now hook this up with the robot. In order to test that, I will go to my e-catalog and under components by manufacturer, visual components and robots, I'll use the same robot again. Enable interfaces. There's a connect workpiece positioner interface where I can start to drag and connect this. You can double check that everything works on the program tab with this jog option to see that you have these joints that the robot is controlling them. Okay, very good. That's about modeling a workpiece positioner. Very similar approach for robot positioner, like a servo track or gantry. So I will just quickly run through that by first importing the geometry. This time my track. I will share these sample geometries on the forum later if you want to practice with the same ones. I will again use the defaults that we used before. It imports nicely, but looks like we didn't get the materials in, or they were not defined in the original model. And what I did quickly there, which you probably didn't notice, is that oftentimes when I model new components, I make sure that my component is in the dead center of the world. So in order to do that, on the modeling tab, make sure you have selected the component, not a feature like this, but the component like this here. And double click that your component properties are shown here and zero out these values. Then you know that your component is in the dead center of the world, and all the other objects, if you see them in the world coordinates, they reflect your component coordinates nicely. Okay, so let's put the materials for this component. So that you can do from tools, assign materials. The workflow here is that you choose the material. So let's say I want to put black. I want this piece to be black. Then I choose aluminum. I want the base plate and that sledge to be aluminum. Then I put some bling on it and I choose chrome. You can select here something and click the press the first letter of the chrome, for in this case C, and it jumps to the material starting with the C. So very easy to find materials like that. So I put chrome here and here, and then I select here and I hit R for red, and it jumps to red. And I put these little thingies here red, because why not? So they are now all colored nicely. Then I can close this panel. Here you can also pick material. So if you don't know what material that is, but you want to use that elsewhere, you can pick the material, then assign it elsewhere. And to clear materials, you can use clear and click the material. So orange in Visual Components world means no material. So assign, there we go. And I will close this. Okay, now we again got just this whole geometry as a one big piece. I will show you now the workflow how to do this with the bigger geometry, even though this is not very heavy geometry. So instead of exploding this into thousands and thousands of features, which could be the case, there's actually also a limit of 1,000 features that it will explode. Otherwise it will tell you to use split command instead. And split command you can use so that you select the feature that you want to split in smaller pieces. You go to tools and split. Then you can choose what you want to include, and you can choose that on the geometry set level or face level or interconnected faces. So if I select these faces and I click one face, it will travel through the 3D model and find all the connected faces. Oftentimes faces and set give you the same result, but not always. So sometimes these faces give you a bit more separation level than geometry set. So I recommend you to test it out. Alright, so I want to include these little thingies also to my selection. So with control I can multi-select them, and also with control you can draw this selection box to select a lot of details in one shot. Alright, with heavier models this might be a little bit labor intensive process, so it takes time, but just to learn to be fast with your navigation and selection, and you will probably nail it pretty fast. Then I hit this split button on the lower right corner, and it splits that geometry out of this geometry. I will rename this as my, I don't know, sledge, for example, and this is rail. Very good. Now same process again. I select this, right click, extract link, or you can do it also here in the tree, right click and extract link. Then the position of this link, again I won't modify it as a hierarchy mode because I would modify that too. I will modify it in selected mode, and I snap it on the center there. Then this joint type won't be fixed. It will be translational. It won't be translational along Z because now it moves up and down. It will be translational along X-axis, which is my red arrow here. And again double check it from the inside here. And this means the positive direction of the axis. So when the joint value increases, the sledge moves here. If you want to invert that, you would choose minus X. So now as the value increases, it will go this way and the minus values would be this way. But I will use now this positive X this way. Again, the controller, I will put new servo controller. Again, new behavior was created here. And then the minimum and maximum values. The minimum value I can set to 0, max value to 4000 because I don't know anything better. We can measure it out with measure tool from there to somewhere here. That seems to be 3400 millimeters, so let's use that instead of 4000. Value expression here means that you can modify the mapping from joint to this movement. So if now my joint moves from 0 to 3400, it will move to the end here. But if I put here, for example, divided by 2, then when the joint value goes to 3400, this geometry would move only halfway here. Or if I would put minus here, it would move halfway here on the opposite direction. So this is where you can, if you want to go advanced and modify the standard mapping, this is where you can do that. Okay, so this is done, except we need to again use the wizard, positioner wizard, this time robot positioner, flange link, link 1, that's okay, and apply. And now we can close it. These wizard tooltips will tell you a little bit what it will do. So if you hover your mouse here a little bit, it gives you a bit more explanation later. And what this wizard now did is that it made us an interface under the link 1 where we can snap the robot. It also created automatically a frame, which is the connection point. I will make my frames visible here. Make sure this is blue and this is selected, then you see your frame, and this is the actual position where the robot will snap. By default it will put that mount frame to the dead center of that link. If you're not happy with that, just select the frame and relocate that before connecting your robot. And now we are ready with this robot positioner. Okay, good. The next one would be end of arm tool. I will use as an example this some sort of a mechanical gripper. And again, I will clear my world first, go to modeling and import. You can also import by just simply dragging a file from your Explorer. In that case, it doesn't ask about importing options. It will use the one ones you used previously. So if you have set up your settings, you can just drag and drop files there to import things fast. Again, I will make sure that my component is in the dead center. And in this case, we see that the origin of that model is not very good. I would like my origin of the component be at the dead center of this cylinder here. In that case, I will take origin snap tool, and I want to define the component origin. Then I need to have, before launching this command, the component selected. If I select some feature here, I would be redefining the origin of that feature. In this case, that's not what I want to do. I want to redefine the origin of this whole component. So I select that here and origin snap. Now if I would snap it simply here, you see that blue arrow coming out like downwards from that face. And I would like this to go upwards so that it will align correctly with the robot. So in the robot end flange, the Z comes out from the end flange of the robot. So I would like here the Z go inside of my gripper. In order to do that, I can flip my align axis before snapping. So I put -Z here. Now you can see that the blue arrow goes inside of the component. I snap it there. That looks good. Before exiting here, I typically put my setting back to this default +C, but that's just my personal preference. And then I hit apply. And now we have the component origin redefined. You can also see that the component location has a little bit changed because everything on the screen stayed in the same place, but the origin is in a new place. So I will zero out this again, so we will get our component in dead center. Now we would like to put these little fingers or whatever we call these to move. So in this case we get this full feature tree here imported. So I don't need to explode or split or anything. I can just use the structure directly from the CAD model. So I will choose this one, right click, extract link. I will make this not this time rotational but translational, not along Z-axis but along -X. I want it to move that way. Alright, then I will say that this is, for example, F1 and the controller is new servo controller, initial value 0, current value 0. You will see that current value changing when you move this. So this value here changes. Reset your simulation and it jumps back to initial value, which is 0 in my case. And the limits, I can eyeball the limit, that how far should it go. Probably 60 millimeters. So the minimum is 0, maximum is 60. Speeds are what they are. I have no idea what they should be at the moment, so I leave them as default. And that's that. Okay, then we need this another finger. So I will select this one, right click, extract link. These are not these are not supposed to be parented to each other, so they will be siblings like this. And you would think that you would like to create a translational link from this, but then that would require also another joint. We want to use that very same joint, so we will make this translational follower. Then we can choose the driver, which is this F1, and now if I move this, the other one moves too. But you can see that it moves in the wrong way because we didn't define correctly this. So I will put plus X, put it in the move mode, so you will see this handle with these arrows. And that looks good. So if I now move this, that one moves. If I move this, that one moves. So they both move in sync now. The other one follows the other one. Okay, very good. Then we will use another wizard end effector. In the end effector wizard, we need to choose the controls for these joints when we connect this with robot. If we put none, it means that we don't care about the controls of these fingers. This would be nice for some simple suction cup gripper where we don't need actually any kinematic controls, or maybe a welding torch where no kinematic should be controlled. But in this case, when we have a mechanical gripper, we want to control that. We can control that joint either as an external axis. If it would be some super nice servo control joint, we would probably use that. But if it's some sort of like a pneumatic axis that it can open and close, I will probably go with the I/O. So I can fire through to close, false to open. I choose controls I/O, I hit apply and close this. And what has happened now is that we have a bunch of behaviors here. So the servo controller appeared when we associated one of the links with the controller, but this interface was made by the wizard, so we can now just simply snap this together with the robot. Again, mount frame was automatically done into the origin of the component, and the script to control that joint, when this signal is fired through, it will close the gripper, and when it signals false, it will open the gripper. And this open and close state are signals that you can follow and monitor. So we have now these which we could connect with the robot. We will see this more in details now in the next webinar when we go to programming. So then we can actually see this guy in action. But now we can simply just double check that it connects correctly. Yep, and we can connect, for example, the action signal output to 50 output. And now if we would fire from robot this to false, this would open. If we fire through, it would close. Quite straightforward. That's about gripper. Now we need to a little bit hurry up because I'm a little bit behind of schedule. So this webinar will be a little bit longer than 1 hour. So I hope you don't mind. And my slides are right here. The next component we're going to model is a conveyor. Again, I won't be saving these, and I will start again by importing the model. Again, I'm happy with the default settings that we have set up already before, so I will simply just drag and drop this. We'll make sure that it's in the dead center. Again, I'm not very happy with the colors because it wasn't defined in the CAD model, so I will go and assign materials. I will take some sort of a material for there, aluminum for the legs, black for those little things, and blue for the sides, because why not? Alright, now in order to create a conveyor, we should first define the frames, how the conveyor path is defined. So in this case we would like to get components from this side, convey them over here on this side, and pass them on to the next component. So what we need first is frames. These frames will define the location for the connection points and also for the path itself. So I can drag from this arrow, hold down my control, and level it together with that face, for example. I will create another frame, call this frame, for example, frame out. Here this frame could be called frame in, and the frame out would be level with that, but maybe project it with control there. So I drag this arrow, hold down control, and snap it with that, and it projects that axis with that. Very good. If I want some gap between the conveyors when I connect them, I could make this overshoot, for example, 20 millimeters. Then there would be 20 millimeter gap. So I put, for example, 5 millimeter gap there like that. Okay, now my frames are in place, and I need behaviors. First behavior that I will need, we need to discuss these behaviors more in details later, because there's a bunch of those, but now I know that I need one-way path. I will create one-way path. Here I can choose the logical maximum capacity. I can choose the name for my behavior. A statistical behavior could be linked here if we had created it first from here. Then it would gather automatically statistical data from this conveyor. Then we can control speeds and things like that. But I will jump to my path definition. Here I expand this GUI item and I hit this plus sign. And I need to choose my frames in correct order. So first in the path there's a frame in and then frame out. And it appears in this list in that order. Then I can close this. If you selected in wrong order, you can reorganize them from these arrows. But it's the top-down order. And here is where you can remove that frame, and here where you can add more. Okay, that's that. Now our path is in place. Then we need interface so that we can connect this component together with other components. We need one-to-one interface. I will call this interface in-interface, and we need a new section. Section is where the actual connected data is defined. So this interface can connect, for example, signals. It can connect tool data from robot to gripper, or from gripper to robot. It can connect joint data from servo track to robot and things like that. But it can also connect material flow, what we are now doing. So in this section we need to define the physical location for the interface, which will be the frame in this location here. Then we here choose the field, which is kind of like selecting what we are actually connecting. We are connecting material flow, so I will choose flow field. We connect the flow to the path input on this side. So you can imagine that the path is something in between this frame and that frame, and when we create the interface here, we connect something to the input of the path, and at this end we need to create another interface to the output of the path. So let's do that. So I will create another interface, this time call this out interface, add new section, section frame is frame out, again a flow type of a field, container is the very same path, the only container we have. This would list all paths what we would have there, but now we have just one, and this time the output. If I go now on the Home tab with plug and play and I reselect the component, I see these little arrows here. If I duplicate this component, it knows that it can connect automatically, and I can connect these like this, and from feeders I can find feeder, and I can connect that with my conveyor, and it seems to work nicely. There's also a wizard for the conveyor, so I will show very quickly how to use that. But it's good to know what happens inside of that wizard, so I showed that step by step. But in order to do the same with the wizard, it is that I select my conveyor or any feature inside of that conveyor. I go to my wizards, conveyor, then I choose auto create on top face the frames, or if I had manually already created the frames, I could choose them from a list, but now the list is not shown because there are no frames. So in this case it will automatically create some frames on the top face. Then you can manually modify the locations if it did wrong guessworking there. Then we can choose the direction. It could go in Y direction, which would be that green arrow, or minus arrow opposing to that, but now we want to follow this red arrow here, so I will choose X. Input connection, we want interface. Output connection, we want an interface. If we had other paths here, we could already automatically connect that with other paths inside of this component, but now we will just create connection interfaces. I'm happy with these settings now, and I go ahead and create conveyor behaviors. You see that these frames appeared there, and also we see that it automatically created the path behavior in an output interface. It also created a sensor interface, so that from processors we can connect there, for example, a sensor and a motor to control whether this is on or off. And also that normal interface to connect together with other conveyors is there. So creating a conveyor with that wizard is pretty straightforward. And now this motor has actually stopped, so I can run the motor there. Alright, that's how you can make a conveyor. Then at the end, couple words about the physics. So Visual Components 4.0 has physics capabilities in it, and we are using physics from NVIDIA for the physics and engine calculations. And how you associate physical behaviors to your components is that you need to define the physical colliders in the geometry, and then you need to add physics behaviors to your component, which will define the frictions and other type of features. When we have geometry in the component, not all of the component geometry need to go to the physics calculation. Typically, some of your geometries are very detailed, and I would make the physical calculation very heavy and slow if you would throw all that detailed geometry for physics engine to calculate. So for that reason, we have a control for what you want to actually include into the physics calculation and what not. And in the feature tree, we can define the colliders. The physics collider means that that part of the feature will go to the physics calculation. Each feature has a selection of non-box, boxes, or precise. And if I simply create now on the modeling tab a new component, and I will add into that new component a new box. I will make this 200 by 200 by 50, and there's this physics. I can expand that and it shows me the collider property. It doesn't have any physical features before I choose something here. So if I choose here, for example, box, it means now that this box block will go to the physics calculations. When I chose here the box, it already created automatically a physics entity. So if I now, for example, elevate this component, it is inside physics calculations. And that box selection means that whatever your shape of that feature is, that it will only put in physics calculation the bounding volume shape. So it will be very lightweight calculation. So even if you have very heavy model and you put that in block mode there, you would get fast calculation, but the accuracy is not very good. And we can see that by if we now create a new component, this time new feature, cylinder. I put this cylinder a little bit more detailed, and I put this as in precise mode. I will elevate my cylinder and rotate that something like that. And now you can see that the cylinder rolls a little bit when it drops. If I put now this block and I check the physics entity behavior, it has some properties here. It has properties about its friction, it has its material density. By default, if you have 0, it means actually that you have 0.2 density. That's not very intuitive, and that's probably going to change in the future. And there's this selection for physics type. In physics means that this selected block is completely in physics, meaning that it will drop on the floor when I hit play. It will collide with other physical objects. If I put it in out of physics, it means that the physical calculation doesn't see this block at all. This is something that you can have this feed behavior in your component, then you can switch on and off this very quickly, for example through Python API. The kinematic mode means that the component will collide with others, but its own position won't be affected by the physics. So for example, you could put robot arm into physics in kinematic mode, and the normal robot controller would calculate the robot arm movement, but the arm could collide with other boxes and things like that. So in this example, it means that that block won't drop, but that cylinder will collide together with the block. And now we can see also that if I change this collider from precise to box for this cylinder, it won't spin because it's actually in the physical world a box. We could then change the friction so it would probably slide and so on. So it means that when you have, for example, for a group of features, let's say you have multiple cylinders like this, and you can multi-select these, right-click and group. It will create a new transform for you, and for this transform you can select, for example, box or boxes or precise. Box means that all the combined bounding volume will go to the physics calculation. Boxes means that every feature underneath there will get its own box, and it will go on that level to physics calculation. So this corner would hit, if a tree would fall on top of this, the tree would hit here, this corner. But if you put it in the precise mode, it will create a convex hull on top of each geometry. Convex hull means basically like a shrink wrap on top of the geometry. So for example, this type of a teapot, the convex hull for that would look something like this. So if you needed this to be more in details in physics, you should separate this nozzle and this handle and maybe this lid and put them all separately in precise mode, the physics. But I recommend you to test it out a little bit. You can create different kind of physics behaviors here. We will cover physics in future tutorials more in details, but I could quickly show you, for example, now if we put this fellow in precise mode, it goes like that. I can make this one a little bit longer. I will create there a new frame, and that frame will go there, and I will create another frame. That frame will go there, so I have frame and frame 1 here, and I can create new behavior physics path. Same way as the previous normal type of a path, I can associate this with frames. So I associate those frames here, and now it has a physics path. And if I wanted this to be colliding with something else, I could put this back to floor level, create a new component, create a new box which is a little bit longer, maybe 50 by 50. A little bit higher. Now you probably get the idea what we're trying to achieve here, so I put a little bit of guidance here. And this box I need to put in physics in box mode. That's the fastest. And if we now simulate this, that will drop also on the conveyor and will be conveyed out. But if I want this to be some sort of a guide rail, I will go to the physics entity behavior, and instead of in physics I would use this kinematic mode. And now it will stay there and it will just simply try to guide that. Now we should use the frictions and things like that to get it nicely slide there, or we could try to help it with using that kind of a shape there. So this is the basics of physics also. So you have the main points are the collider selection in the features, and then the physics behaviors in the behaviors list. There's also physics cable and physics joint behaviors which come handy in other applications, but those can be then discussed later. This is pretty much the content for today. I apologize for this taking a bit longer, and a couple of short force closes during the session. Those will be addressed soon with the new release. Here's an interesting video showing off just some physical capabilities. Very useless layout, but fun. Only thing I'm missing here is the sounds, so maybe I will need to dive into Python scripting and do that. Okay, I thank you for watching this, and there will be soon new webinar about robot programming. This will be shared on forum.visualcomponents.com, so check it out later there, and stay tuned for more.